Hey there, how was your day? Wherever you are in the world, whatever time it is, I'm so glad you found your way here tonight. We're about to embark on a journey that will challenge everything you think you know about our planet's history, about civilization itself, and about humanity's place in the grand timeline of Earth. Tonight, we're diving deep into one of the most fascinating and quietly unsettling questions in all of science. What if we aren't the first? What if, millions of years before humans ever walked upright, before we built our first cities or carved our first tools, another civilization already called this planet home? What if everything we consider uniquely human, uniquely ours, has happened before? I'd love to know where you're listening from tonight. Feel free to comment your time and location below. If you find comfort in these gentle explorations of deep scientific mysteries, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious minds like ours, souls who aren't afraid to ask the big questions, the uncomfortable questions that make us reconsider our place in the cosmic story. Tonight, we are featuring Punk Rocks. He says the day is just starting for him, and he loves listening to our videos at the gym. That's really cool to know. The visuals are here for you, a bit darker as you all suggested in the poll. Do consider participating in them, as we really anticipate every member of our channel and consider every feedback. Feel free to close your eyes now, breathe deep, and let your imagination drift through deep time itself. There's absolutely no problem if you doze off midway through this exploration. Sometimes the most profound insights come when we're floating on the edge of consciousness, when our rational minds relax enough to consider possibilities we normally wouldn't dare entertain. What we're about to explore tonight is called the Silurian Hypothesis, named not after some ancient alien race, but after a fictional species from the British science fiction series Doctor Who. The Silurians, in that show, were an intelligent reptilian species that evolved on Earth millions of years before humans. They built cities, developed technology, and considered themselves the rightful inhabitants of this world long before mammals ever climbed down from the trees. But here's what makes this more than just science fiction. What makes it a legitimate scientific hypothesis that researchers at NASA and other institutions are seriously investigating. The question isn't whether lizard people once ruled the Earth. The question is far more subtle, far more profound, and in many ways, far more unsettling. The question is this: if an industrial civilization had existed on Earth millions of years ago, would we even be able to detect it? Would there be any trace left for us to find? Any signature in the geological record that would whisper to us across the vast gulf of deep time, telling us we weren't the first to harness fire, to build cities, to fundamentally alter the chemistry of our planet's atmosphere? Think about this for a moment. Human industrial civilization has existed for roughly 300 years. That's not 300,000 years or 300 million years. Just 300 years since we began burning coal and oil on an industrial scale, since we started fundamentally changing the composition of Earth's atmosphere, since we began what geologists are now calling the Anthropocene, the age of humans, but Earth is 4.6 billion years old. If you compressed all of Earth's history into a single year, human industrial civilization would represent the last few seconds before midnight on December 31st. We are the newest arrivals at a party that's been going on for eons. We've only just walked through the door, and yet we assume we're the first guests to arrive. This assumption, this quiet arrogance, is what the Silurian Hypothesis challenges, not by claiming that ancient civilizations definitely existed, but by asking a far more humble question. How would we know if they had? You see, when most people think about ancient civilizations, they think about permanence. They think about the pyramids, about Stonehenge, about structures built to last forever. But here's the uncomfortable truth. that archaeologists and geologists understand all too well. Almost nothing lasts forever on geological timescales. Consider the oldest human structures we know of. The pyramids of Giza are roughly 4,500 years old. Impressive by human standards, but barely a blink of an eye in geological terms. Even if these monuments were made of the most durable materials imaginable, even if they were built to withstand everything nature could throw at them, they would be completely erased by natural processes in just a few million years. Erosion doesn't care about human ambition. Wind and water and ice don't respect our desire for immortality. The Earth itself is constantly recycling, constantly churning, constantly erasing the evidence of what came before. The seafloor, where much of our industrial waste ends up, is completely recycled every 200 million years through the process of plate tectonics. The continents themselves drift and collide and break apart, grinding ancient landscapes into dust. So if a civilization existed 50 million years ago, or 100 million years ago, what would be left? What traces could survive the relentless recycling of our dynamic planet? This is where the Silurian hypothesis becomes genuinely fascinating, genuinely scientific. Because while stone monuments and metal artifacts might not survive, chemical signatures can. Isotope ratios can. Changes in the composition of ancient atmospheres, preserved in ice cores and sediment layers, can whisper secrets across millions of years. When we burn fossil fuels, we're not just releasing carbon dioxide. We're releasing carbon that has a very specific isotopic signature, a kind of chemical fingerprint that's different from the carbon that cycles naturally through the atmosphere. This signature shows up in tree rings, in ice cores, in the shells of marine organisms. It's our industrial autograph, written in the language of chemistry across the face of our planet. But here's the thing that keeps scientists up at night, the thing that makes the Silurian hypothesis more than just an interesting thought experiment. We've found isotopic anomalies in the geological record, sudden spikes in atmospheric carbon dioxide that happened millions of years ago, rapid changes in ocean chemistry that seem to mirror what we're doing to our planet right now. Most of these anomalies have perfectly natural explanations: massive volcanic eruptions, asteroid impacts, natural climate cycles that we're still trying to understand. But some of them are harder to explain. Some of them look suspiciously like what we might expect to see if an industrial civilization had existed in the distant past. The Paleocene-Eocene thermal maximum, for instance. About 56 million years ago, something caused a massive release of carbon into the atmosphere. Global temperatures rose by 5 to 8 degrees Celsius in just a few thousand years. The oceans became acidic. Many species went extinct. It looks remarkably similar to what climate scientists predict will happen if we continue burning fossil fuels at our current rate. What caused this ancient warming event? The leading theory is that massive volcanic activity in the North Atlantic released enormous amounts of carbon dioxide and methane. But the isotopic signature is strange, complex, hard to explain with volcanism alone. Some researchers have suggested that methane hydrates on the ocean floor were destabilized, releasing their carbon into the atmosphere in a runaway greenhouse effect. But what if there's another explanation? What if, 56 million years ago, another civilization faced the same choice we're facing now? What if they too discovered fossil fuels, built their cities, filled their skies with carbon dioxide, and triggered their own version of climate change? This is the kind of question that makes scientists uncomfortable, and rightfully so. Science is built on evidence, on observation, on testable hypotheses, and the evidence for ancient industrial civilizations is at best circumstantial. At worst, it's non-existent. But that's exactly what makes the Silurian hypothesis so important. It's not asking us to believe in ancient aliens or lost Atlantean technologies. It's asking us to confront the limits of our knowledge, the gaps in our understanding of deep time. It's asking us to consider what traces our own civilization will leave and whether those traces would be detectable millions of years from now. Think about it this way. If human civilization disappeared tomorrow, if every city crumbled and every road was reclaimed by forest, what would remain after 10 million years? Our plastic waste might survive in certain conditions, compressed into thin layers in sedimentary rock. The isotopic signature of our fossil fuel burning would be preserved in ice cores and marine sediments. But would future geologists be able to tell the difference between our industrial signature and a natural catastrophe? This is where the hypothesis becomes a mirror, reflecting back our own assumptions about permanence, about significance, about our place in the grand story of Earth. We assume that intelligence is rare, that consciousness is precious, that we are the first and perhaps the only beings to look up at the stars and wonder about our place in the universe. But what if intelligence isn't as rare as we think? What if consciousness, like life itself, is an emergent property that arises naturally given enough time and the right conditions? What if the story of Earth isn't the story of one species slowly awakening to awareness, but the story of many species, many civilizations, each thinking they were the first, each leaving their own subtle signature in the chemical memory of stone and ice? The Silurian hypothesis doesn't require us to believe that dinosaurs built cities or that ancient mammals developed space travel. It simply asks us to consider the possibility that intelligence, like extinction, might be cyclical. That consciousness might arise, flourish, and fade many times over the course of our planet's long history. And if that's true, if we're not the first to gaze up at the stars and wonder about our cosmic significance, then what does that mean for us? What does it mean for our future, our legacy, our responsibility to the planet we call home? These are the questions that will guide us through this exploration. Questions that challenge our assumptions about uniqueness, about permanence, about the very nature of intelligence itself. We're not here to prove that ancient civilizations existed. We're here to understand what it would mean if they had, and what that possibility teaches us about ourselves. As you settle deeper into this journey through deep time, remember that you're part of an unbroken chain of consciousness that stretches back through millions of years of evolution. The atoms in your body were forged in the hearts of ancient stars. The oxygen you breathe was exhaled by countless generations of plants and algae. The very awareness that allows you to contemplate these mysteries emerged from billions of years of natural selection, of complexity building upon complexity, of the universe slowly awakening to itself. Whether we're the first civilization to ponder these questions or the latest in a long line of conscious beings, we are here now, aware now, responsible now for the choices we make and the legacy we leave. The Silurian hypothesis isn't just about the past. It's about the future, about the traces we'll leave, about the story future archaeologists might tell about us millions of years from now. Will they find evidence of a species that learned to harness the power of atoms, that sent signals across the electromagnetic spectrum, that briefly flickered with the light of consciousness before fading into the geological record? Or will they find something else entirely, a signature we haven't even imagined yet? Tonight, we begin to explore these possibilities, to journey back through deep time in search of shadows and whispers, chemical fingerprints and isotopic ghosts. We're about to discover that the question isn't whether we can prove ancient civilizations existed. The question is whether we can prove they didn't. The search for evidence of ancient civilizations forces us to think like cosmic detectives, piecing together clues that have been scattered across millions of years of geological upheaval. But unlike the crime scenes we see in movies, where evidence is preserved behind yellow tape and protected from contamination, the Earth itself is the ultimate destroyer of evidence. Imagine trying to solve a mystery where the crime scene has been hit by earthquakes, floods, volcanic eruptions, and ice ages, where the floor has been completely replaced dozens of times, where the walls have been torn down and rebuilt, where even the air has been recycled countless times through the lungs of billions of organisms. This is the challenge facing scientists who dare to ask whether we might not be alone in Earth's history. Dr. Gavin Schmidt, a climate scientist at NASA's Goddard Institute for Space Studies, was having lunch with astrophysicist Adam Frank when this question first began to take serious scientific shape. They weren't discussing ancient aliens or lost civilizations. They were talking about something far more practical and immediate. They were trying to understand how to search for signs of industrial civilizations on distant planets. Think about it from their perspective. We're spending billions of dollars building telescopes designed to detect Earth-like planets around other stars. We're developing techniques to analyze the atmospheres of these distant worlds, looking for chemical signatures that might indicate the presence of life, or even better, the presence of intelligence. But here's the problem that kept nagging at them. How would we recognize an industrial civilization from space? What would be the telltale signs? The smoking guns that would announce to the universe that a planet hosts not just life, but intelligent life capable of reshaping its environment? The obvious answer is atmospheric composition. Industrial civilizations burn things. They release carbon dioxide, methane, nitrogen compounds, artificial chemicals that wouldn't exist in nature. They change the very air they breathe, often in ways that make that air less suitable for breathing. But then Schmidt and Frank realized something unsettling. If we're having trouble figuring out how to detect industrial civilizations on other planets, how confident can we be that we would recognize the signs of industrial civilizations on our own planet if they had existed in the deep past? This is where their lunch conversation took an unexpected turn. Instead of looking outward to the stars, they decided to look backward through time. Instead of asking how we might detect aliens, they began asking how future scientists might detect us. The exercise was meant to be hypothetical, a thought experiment designed to sharpen their techniques for studying distant worlds. But the more they dug into the question, the more complex and fascinating it became. Because it turns out that detecting the traces of ancient civilizations is far more difficult than you might imagine. Let's start with the most obvious signatures. Industrial civilizations produce waste, lots of it. We filled landfills with our discarded technology, buried billions of tons of garbage, scattered plastic debris across every ocean. Surely these waste products would leave clear evidence for future archaeologists to discover. But here's where deep time becomes our enemy. Those landfills, those plastic islands, those carefully constructed waste sites are all located on the Earth's surface or in shallow waters. And the Earth's surface is the most unstable, most constantly changing part of our planet. Consider what happens to a typical landfill over geological time. First, the organic waste decomposes, leaving behind a mixture of synthetic materials and heavy metals. These materials might be compressed into sedimentary layers as new deposits accumulate on top. But then the real recycling begins. Plate tectonics ensures that continental surfaces are constantly being uplifted, eroded, and redeposited. Mountain ranges rise and fall. Rivers change course, carving new valleys and filling old ones. Ice ages advance and retreat, scouring the landscape and redistributing sediments across vast distances. Most dramatically, the ocean floors, where much of our waste ultimately ends up, are completely recycled every 200 million years. The seafloor spreads at mid-ocean ridges, travels across ocean basins, and is eventually subducted back into the Earth's mantle at deep-sea trenches. It's like a giant conveyor belt that carries evidence into the planet's interior, where it's melted and mixed and eventually recycled into new rock. So after 100 million years, most of our landfills, most of our cities, most of our physical infrastructure would be completely gone. Not just buried or hidden, but literally recycled back into the basic materials of the planet. This is a humbling realization. We build our monuments to last, carve our names in stone, create time capsules for future generations, but on geological timescales, even our most permanent achievements are as ephemeral as sandcastles at high tide. But wait, you might say, what about our most durable creations? What about materials that are specifically designed to resist degradation? What about nuclear waste, for instance, with half-lives measured in thousands or even millions of years? This is where the picture becomes slightly more hopeful for future archaeologists. Some of our synthetic materials might indeed survive long enough to leave traces in the geological record. Plastics, under the right conditions, could be preserved in sedimentary rocks. The isotopic signatures of our nuclear activities might be detectable in certain mineral deposits. In fact, geologists have already found evidence of our nuclear age preserved in the environment. The atomic bomb tests of the 1940s and 1950s scattered radioactive isotopes across the globe. These isotopes have settled into sediment layers and will remain detectable for millions of years. Future geologists will be able to identify a thin layer in the rock record that marks the moment when one species on Earth learned to split atoms. But here's the crucial question. Would these traces be obviously artificial? Would they clearly indicate the presence of an intelligent civilization? Or could they be explained by natural processes? This is where the Silurian hypothesis becomes genuinely challenging. Because the more we understand about natural processes, the more we realize that nature is capable of producing some surprisingly artificial-looking signatures. Take carbon isotopes, for instance. When we burn fossil fuels, we're releasing carbon that was locked away millions of years ago when ancient plants and marine organisms were buried and compressed into coal and oil. This ancient carbon has a distinctive isotopic signature that's different from the carbon currently cycling through the atmosphere. When we release this carbon by burning fossil fuels, we change the isotopic composition of atmospheric carbon dioxide. This change is detectable in tree rings, ice cores, and marine sediments. It's one of the clearest signatures of our industrial activity. But natural processes can also change atmospheric carbon isotope ratios. Massive volcanic eruptions can release carbon with unusual isotopic signatures. The decomposition of methane hydrates on the ocean floor can flood the atmosphere with carbon that looks suspiciously similar to fossil fuel carbon. So if future geologists found evidence of unusual carbon isotope ratios in ancient sediments, how would they know whether they were looking at evidence of an ancient civilization or just another natural climate event? This ambiguity extends to almost every potential signature of industrial activity. Unusual concentrations of heavy metals could be volcanic activity or asteroid impacts. Rapid changes in atmospheric composition could be natural climate cycles or ecological collapses. Even artificial chemicals might have natural analogues that we haven't discovered yet. The more Schmidt and Frank investigated this question, the more they realized that the geological record is like a very noisy communication channel. The signal of ancient civilizations, if it exists at all, would be embedded in a background of natural variability that spans millions of years and includes some truly dramatic events. Asteroid impacts have changed atmospheric chemistry more dramatically than human industry ever has. Massive volcanic eruptions have released more carbon dioxide in single events than we've managed to produce in centuries of burning fossil fuels. Natural climate cycles have driven species extinctions that dwarf anything in recorded human history. Against this background of natural catastrophes and slow geological processes, the signature of an industrial civilization might be surprisingly subtle. It might require extremely careful analysis to distinguish from natural phenomena, and it might only be detectable for a limited window of time before natural processes erased or obscured the evidence. This realization led to a startling conclusion. If we're having trouble figuring out how to detect our own civilization in the geological record, then we might be missing evidence of ancient civilizations that already exists. Not because that evidence is obvious and we're ignoring it, but because it's subtle and we don't know how to recognize it. We might be looking at chemical signatures in ancient rocks that represent the industrial activities of long-vanished civilizations, but interpreting them as natural phenomena because we don't have the conceptual framework to recognize artificial signatures that old. This is the heart of the Silurian hypothesis. Not the claim that ancient civilizations definitely existed, but the recognition that our methods for detecting them are probably inadequate. We're like archaeologists trying to study ancient cultures, but we're limited to tools that can only detect evidence less than a few hundred years old. Think about how this changes our perspective on deep time. We've been assuming that the absence of evidence for ancient civilizations is evidence of their absence. But what if it's simply evidence of our limitations? What if the Earth is full of subtle signatures that we're misinterpreting because we don't yet understand how industrial civilizations age in geological time? This possibility is both exciting and unsettling. Exciting because it suggests that intelligence might be far more common in the universe than we've assumed. If consciousness and civilization can arise multiple times on a single planet, then the cosmos might be teeming with intelligence, each species assuming they're unique just as we do. But it's also unsettling because it challenges our assumptions about permanence and significance. We want to believe that human civilization is special, that our achievements will endure, that we're building something that will outlast the ages. The Silurian hypothesis suggests that even the most successful civilizations might leave only the faintest traces, whispers in stone that future scientists might mistake for natural phenomena. As you drift deeper into contemplation of these vast timescales, consider what this means for our own legacy. If we disappeared tomorrow, what would remain? What signature would we leave in the geological record? And more importantly, what does this teach us about how we should live, how we should treat our planet, how we should think about our responsibilities to the future? The search for ancient civilizations isn't just about the past. It's about understanding our place in the long story of consciousness on Earth, and about recognizing that our time here, however brief, is part of something much larger and more mysterious than we've ever imagined. The deeper we venture into this mystery, the more we realize that we're not just searching for evidence of ancient civilizations. We're confronting the fundamental limits of knowledge itself, the boundaries of what can be known across the vast expanses of geological time. Consider for a moment the sheer audacity of what we're attempting. We're trying to detect the activities of hypothetical beings who lived tens of millions of years ago, whose entire civilizations rose and fell long before the first mammals learned to use tools, long before the first flowers bloomed, long before the continents had even drifted into their current positions. It's like trying to read a book that's been buried under a mountain, burned in a fire, dissolved in acid, frozen in ice, and then rewritten by 1,000 different authors who had no idea what the original text contained. And yet, this is exactly what Earth's geological processes do to the evidence of past events. But here's where the story becomes even more intriguing. Because while most physical evidence of ancient civilizations would be erased by geological processes, there are certain signatures that might persist, certain fingerprints that could survive the recycling of continents and the churning of ocean floors. The key lies in understanding which traces are most likely to survive deep time. And paradoxically, it's not the grand monuments or the impressive technologies that would endure. It's the waste products, the unintended consequences, the subtle chemical changes that industrial civilizations inevitably leave in their wake. When we burn fossil fuels, we're not just releasing energy. We're fundamentally altering the carbon cycle that has regulated Earth's climate for millions of years. We're taking carbon that was safely locked away in underground deposits and releasing it into the atmosphere faster than natural processes can absorb it. This creates what scientists call a carbon isotope excursion, a sudden shift in the ratio of different carbon isotopes that shows up in sedimentary layers, ice cores, and the shells of marine organisms. It's like a chemical signature written in the language of atoms, a message that says something unusual happened to the carbon cycle at this particular moment in Earth's history. But here's what makes this signature so fascinating from the perspective of the Silurian hypothesis. We've found similar isotope excursions in the geological record, moments when the carbon cycle seemed to go haywire, when atmospheric carbon dioxide levels spiked dramatically, when ocean chemistry changed in ways that mirror what we're doing to our planet today. The most famous of these events is the Paleocene-Eocene thermal maximum, which occurred about 56 million years ago. Something caused a massive release of carbon into the atmosphere. Global temperatures rose by 5 to 8 degrees Celsius. The oceans became acidic. Many species went extinct. It was, in many ways, a preview of what climate scientists predict will happen if we continue our current trajectory. What caused this ancient warming event? The leading scientific explanation involves massive volcanic activity in the North Atlantic, combined with the destabilization of methane hydrates on the ocean floor. It's a perfectly reasonable natural explanation for a dramatic natural event, but the isotopic signature is complex, puzzling, not quite what we would expect from volcanism alone. Some researchers have proposed additional mechanisms: comet impacts that vaporized carbon-rich rocks, massive wildfires that burned for centuries, even the sudden release of methane from Arctic permafrost as the planet warmed. Each of these explanations is scientifically plausible. Each fits some aspects of the evidence while leaving others unexplained. But what if we're missing a simpler explanation? What if the Paleocene-Eocene thermal maximum wasn't caused by any single natural catastrophe, but by the same process that's driving climate change today? What if 56 million years ago, another civilization discovered fossil fuels? This is where the Silurian hypothesis moves from abstract possibility to concrete speculation. Because if an ancient civilization had undergone their own industrial revolution, if they had burned their way through underground deposits of coal and oil, they would have created exactly the kind of carbon isotope excursion we see in the geological record. The timeline would even make sense. The Paleocene-Eocene thermal maximum occurred during a period when Earth's climate was already warm, when forests covered much of the planet, when conditions might have been ideal for the evolution of large-brained species capable of developing technology. And the aftermath of the event, the gradual recovery of the carbon cycle over hundreds of thousands of years, matches what we might expect if an industrial civilization had exhausted their fossil fuel reserves and then disappeared, leaving natural processes to slowly rebalance atmospheric chemistry. But this is where we must be careful, because the temptation to see patterns where none exist is one of the greatest dangers in any scientific investigation. The human mind is exquisitely evolved to detect patterns, to find meaning in chaos, to construct narratives that make sense of complex data. And the story of ancient civilizations is an incredibly appealing narrative. It speaks to our deepest fears about our own fragility, our own potential for self-destruction. It offers a kind of cosmic companionship, the comforting idea that we're not alone in our struggles with technology and environmental change. But science demands more than appealing narratives. It demands evidence, reproducible observations, testable hypotheses. And the evidence for ancient industrial civilizations remains frustratingly ambiguous. The carbon isotope excursions we see in the geological record can all be explained by natural processes. The rapid climate changes, the mass extinctions, the chemical signatures that seem so artificial, all have perfectly reasonable natural explanations. This doesn't mean the Silurian hypothesis is wrong. It means we're operating at the very limits of what the geological record can tell us. We're trying to extract information that may not be extractable, to read messages that may not exist. But that limitation itself tells us something profound about our own civilization and its potential legacy. If we're having trouble detecting the traces of hypothetical ancient civilizations, what does that say about the traces we're leaving? This question has become increasingly urgent as we grapple with our own impact on the planet's climate and ecosystems. We're conducting what amounts to a massive geological experiment, altering atmospheric chemistry faster than it's been altered in millions of years, driving species extinct at rates that rival the great mass extinctions of the past. Future geologists will certainly be able to detect our presence in the rock record. The isotopic signature of our fossil fuel burning, the radioactive fallout from our nuclear weapons, the plastic debris scattered across the ocean floors, All of these will leave traces that persist for millions of years. But will these traces be obviously artificial? Will they clearly indicate the presence of an intelligent civilization? Or will they look like just another natural catastrophe in Earth's long history of natural catastrophes? Consider our most dramatic impact on the planet. We're currently driving what many scientists consider the sixth mass extinction in Earth's history. Species are disappearing at rates that are hundreds or thousands of times higher than natural background extinction rates. This biological signature will certainly be preserved in the fossil record. Future paleontologists will be able to identify a moment when biodiversity suddenly collapsed, when ecosystems that had been stable for millions of years suddenly reorganized themselves around a much smaller number of surviving species. But mass extinctions are natural phenomena. Earth has experienced them before, and they've always been followed by periods of evolutionary recovery and diversification. Would the pattern of extinctions we're causing look obviously different from previous natural mass extinctions? The answer isn't clear. While our impact on the planet is unprecedented in its speed and scope, it might not be unprecedented in its ultimate signature. Previous mass extinctions have also involved rapid climate change, ocean acidification, and the collapse of complex ecosystems. This ambiguity extends to almost every aspect of our industrial legacy. We're changing the planet in dramatic ways, but many of those changes might be indistinguishable from natural processes when viewed across geological timescales, which brings us back to the central challenge of the Silurian hypothesis. We're not just trying to detect ancient civilizations, we're trying to understand what makes a civilization detectable across deep time. We're trying to figure out what kinds of signatures can survive the Earth's relentless recycling processes. And in doing so, we're forced to confront uncomfortable questions about our own significance, our own permanence, our own assumptions about what it means to leave a lasting mark on the world. Perhaps the most unsettling aspect of the Silurian hypothesis isn't the possibility that ancient civilizations existed. It's the possibility that they existed and then vanished so completely that we can barely detect their presence. It's the suggestion that even the most successful, most advanced civilizations might be ultimately ephemeral, their achievements lost to the slow grinding of geological time. This perspective challenges our most fundamental assumptions about progress, about permanence, about the meaning of civilization itself. We want to believe that intelligence is cumulative, that each generation builds on the achievements of the previous one, that consciousness represents an arrow pointing toward ever greater complexity and understanding. But what if consciousness is more like a candle flame, flickering briefly in the darkness before being extinguished by forces beyond its control? What if the story of intelligence on Earth isn't a single upward trajectory, but a series of separate experiments, each rising and falling according to its own internal logic? These questions don't have easy answers. They may not have answers at all, but they force us to think more carefully about our relationship with deep time, about our responsibilities to future generations, about the kinds of traces we want to leave for whatever intelligences might follow us. As you settle deeper into contemplation of these vast possibilities, consider what it means to be conscious in a universe where consciousness itself might be transient. What does it mean to care about the future when the future extends far beyond anything we can meaningfully influence? What does it mean to seek permanence in a cosmos built on constant change? The Silurian hypothesis doesn't provide answers to these questions, but it does something perhaps more valuable. It reminds us that we are part of a story much larger and stranger than we typically imagine. Whether we're the first chapter in that story or the latest in a long series, we are here now, aware now, responsible now for the choices we make and the legacy we leave. And in that responsibility, in that moment of awareness, we touch something that transcends the mere passage of geological time. We participate in the universe's ongoing experiment with consciousness, adding our own small voice to whatever cosmic conversation has been taking place across the eons. But perhaps the most intriguing aspect of searching for ancient civilizations lies not in what we might find, but in what the search itself reveals about the nature of intelligence and technology. Because as we dig deeper into this mystery, we begin to realize that our assumptions about how civilizations develop, how they use resources, and how they interact with their environment might be fundamentally limited by our own experience. We tend to think of industrial civilization as following a predictable pattern. First comes agriculture, then cities, then the discovery of fossil fuels, then rapid technological advancement. We assume that any intelligent species would follow roughly the same trajectory we have, burning coal and oil, building cities of steel and concrete, filling the atmosphere with carbon dioxide as they pursue ever greater energy consumption. But what if this assumption is wrong? What if our particular path toward industrialization is just one of many possible routes that intelligence might take? What if other civilizations developed along entirely different lines, using technologies and energy sources that would leave completely different signatures in the geological record? Consider the possibility of a civilization that never discovered fossil fuels, or discovered them but chose not to use them. Perhaps they developed solar technology millions of years before we did, harnessing the sun's energy directly instead of burning ancient sunlight stored in coal and oil. Perhaps they built their cities from organic materials that would decompose completely, leaving no trace for future archaeologists to discover. Or imagine a civilization that developed biotechnology instead of mechanical technology. Instead of building machines from metal and plastic, they might have engineered living organisms to serve their needs. Biological computers, organic transportation systems, living buildings that grew rather than being constructed. Such a civilization might have had an enormous impact on the planet's ecosystems while leaving almost no recognizable artifacts. This possibility becomes even more intriguing when we consider the timescales involved. Life has existed on Earth for nearly 4 billion years. Complex multicellular organisms have been around for over 600 million years. Intelligence, in the form of complex nervous systems, capable of learning and problem-solving, has existed for hundreds of millions of years. We humans tend to think of intelligence as rare, as something that requires very specific conditions to evolve. But what if we're wrong? What if intelligence is actually relatively common, arising naturally whenever organisms face complex environmental challenges over sufficient periods of time? The fossil record shows us that sophisticated behaviors have evolved many times independently. Tool use has been documented in various species of birds, mammals, and even some invertebrates. Social organization, communication systems, even primitive forms of agriculture have appeared across different lineages throughout evolutionary history. Most remarkably, we now know that some species have developed what can only be called proto-technologies. Certain species of birds use tools not just to obtain food, but to make other tools. Some primates have entered what anthropologists recognize as their own Stone Age, using rocks to crack nuts and shape other implements. Even some cephalopods have been observed using tools and displaying problem-solving abilities that rival those of vertebrates. If such behaviors can evolve independently in multiple lineages, what might happen given enough time? What might a species accomplish if it had not thousands of years to develop technology, but millions? What if intelligence had more time to develop than we've assumed? This question becomes particularly fascinating when we consider the periods in Earth's history when conditions might have been ideal for the evolution of large-brained, technologically capable species. During the Cretaceous period, for instance, from about 145 to 66 million years ago, Earth's climate was warm and stable. Lush forests covered much of the planet. Atmospheric oxygen levels were high, potentially supporting larger, more energy-intensive brains. This was the age of dinosaurs, but not just the massive predators and herbivores we typically imagine. The Cretaceous also saw the evolution of highly intelligent dinosaur species. Troodon, for instance, had a brain-to-body ratio comparable to that of modern birds, along with large eyes, grasping hands, and sophisticated pack-hunting behaviors. What if species like Troodon had continued evolving for another 50 million years instead of being wiped out by the asteroid impact that ended the age of dinosaurs? What if they had developed opposable thumbs, complex language, the ability to control fire? What kind of civilization might have emerged from a lineage that had already demonstrated remarkable intelligence and social cooperation? The more we learn about dinosaur behavior and cognition, the more plausible this scenario becomes. Recent discoveries have revealed that many dinosaur species engaged in sophisticated social behaviors. They built nests, cared for their young, engaged in complex mating displays, and some even appear to have used tools. We've found evidence of dinosaur species that buried their dead, suggesting some form of ritual behavior or at least recognition of death as a significant event. We've discovered fossilized dinosaur tracks that show evidence of coordinated group hunting, with different species working together to bring down prey. Most intriguingly, we've found what appear to be dinosaur art, scratches and markings on rocks that don't appear to serve any obvious survival function, but which show evidence of intentional design and aesthetic consideration. If dinosaurs were capable of creating art 100 million years ago, what else might they have been capable of? But even if we accept the possibility that highly intelligent dinosaur civilizations might have existed, we still face the same fundamental problem that makes the Silurian hypothesis so challenging. How would we detect their presence after 66 million years of geological activity? This is where the search for ancient civilizations begins to resemble detective work on an almost impossibly cold case. We're looking for clues that have been buried, eroded, subducted, and recycled through geological processes that operate on timescales that dwarf human comprehension. But there are certain signatures that might survive even these processes, certain types of evidence that could persist across tens of millions of years, waiting for scientists clever enough to recognize their significance. One possibility lies in the realm of isotopic geochemistry. Different industrial processes create characteristic isotopic signatures that can persist in sedimentary rocks for extremely long periods. The ratio of different uranium isotopes, for instance, can reveal whether uranium was ever concentrated and purified for use in nuclear technology. Similarly, the isotopic composition of various metals can reveal whether they were ever extracted, refined, and concentrated by industrial processes. Even if all physical artifacts have been destroyed, the chemical fingerprint of metallurgy might persist in mineral deposits and sedimentary layers. Another possibility involves what geologists call stratigraphic anomalies, unusual concentrations of rare elements that appear suddenly in the geological record and then disappear just as quickly. Most such anomalies have natural explanations, usually involving volcanic activity or asteroid impacts, but some remain mysterious, showing patterns that don't quite fit any known natural process. The iridium layer that marks the end of the Cretaceous period, for instance, was initially puzzling to geologists. This thin layer of clay, enriched with the rare metal iridium, appears in sedimentary rocks all over the world at exactly the time when dinosaurs went extinct. The mystery was solved when scientists realized that the iridium came from the asteroid that struck Earth 66 million years ago. But what if we found similar anomalies that couldn't be explained by impacts or volcanism? What if we discovered layers enriched with metals like platinum, palladium, or rare earth elements in concentrations and patterns that suggested deliberate extraction and processing? Such discoveries would require extremely careful analysis to distinguish from natural phenomena, but they might represent the only surviving evidence of ancient industrial activities, chemical fossils of civilizations that vanished long before the first human ancestors learned to use fire. The search for such evidence is just beginning. Most geological surveys have focused on understanding natural processes rather than looking for artificial signatures. But as our analytical techniques become more sophisticated, as our understanding of isotopic chemistry deepens, we may begin to recognize patterns that previous generations of scientists missed. This possibility is both exciting and sobering. Exciting because it suggests that we might not be alone in the cosmos, that intelligence might be far more common than we've assumed. But sobering because it reminds us of our own fragility, our own potential impermanence. If ancient civilizations did exist and then vanish, leaving only the faintest chemical traces, what does that say about our own prospects for long-term survival? What does it suggest about the challenges that any technological civilization must eventually face? Perhaps the most profound insight of the Silurian hypothesis is not about the past, but about the future. It forces us to think seriously about our own legacy, about the traces we're leaving, about the kinds of signatures that might survive our own eventual disappearance. We're currently conducting what amounts to a planetary scale experiment, altering Earth's atmosphere and climate in ways that haven't occurred for millions of years. We're creating new chemical compounds that have never existed in nature, scattering radioactive isotopes across the globe, driving species extinct at rates that rival the great mass extinctions of the past. All of these activities will leave traces in the geological record. Future scientists will be able to identify the moment when one species learned to split atoms, when atmospheric carbon dioxide levels began rising exponentially, when the diversity of life on Earth suddenly collapsed. But will these traces be obviously artificial? Will they clearly indicate the presence of an intelligent civilization, or will they look like just another natural catastrophe in Earth's long history of environmental upheavals? The answer depends partly on how long our civilization persists, and what choices we make about our relationship with the planet. If we learn to live sustainably, if we develop technologies that work in harmony with natural systems rather than against them, we might leave a very different signature than we're currently creating. But if we continue on our current trajectory, if we exhaust our resources and destabilize our environment, we might join whatever ancient civilizations may have preceded us. Our cities would crumble, our monuments would erode, our plastic waste would be compressed into thin layers in sedimentary rock. Future geologists might find evidence of our brief industrial age in the form of unusual isotope ratios and trace element concentrations. They might puzzle over the sudden spike in atmospheric carbon dioxide that occurred in the late 20th and early 21st centuries. They might wonder what caused the mass extinction that eliminated so many species in such a short period of time. But would they recognize these signatures as evidence of intelligence, or would they develop natural explanations? Just as we've developed natural explanations for the mysterious events we see in the ancient geological record. This uncertainty brings us full circle to the central challenge of the Silurian hypothesis. We're not just searching for evidence of ancient civilizations. We're trying to understand what makes any civilization detectable across the vast expanses of geological time. And in doing so, we're forced to confront fundamental questions about the nature of intelligence, the inevitability of technological development, and the ultimate fate of consciousness in a universe governed by entropy and change. These questions don't have easy answers. They may not have answers at all, but they remind us that we are part of something much larger and more mysterious than our everyday experience suggests. Whether we're the first intelligent species to evolve on Earth or the latest in a long line of conscious beings, we are here now, aware now, responsible now for the choices we make and the legacy we leave. As you drift deeper into contemplation of these cosmic possibilities, remember that you're witnessing one of the most remarkable phenomena in the known universe. Consciousness arising from matter, awareness emerging from complexity, intelligence pondering its own existence, and wondering about its place in the grand story of space and time. The atoms that make up your body were forged in the hearts of ancient stars. The oxygen you breathe was exhaled by countless generations of plants and algae. The very thoughts you're thinking now represent the culmination of billions of years of evolution, of natural selection gradually building complexity upon complexity, until matter itself became capable of contemplating its own origins. Whether this has happened before, whether it will happen again, whether consciousness is rare or common in the cosmos, one thing remains certain. This moment of awareness, this capacity to wonder and question and imagine, is among the most precious things in the known universe. And in protecting that capacity, in nurturing it, and passing it on to future generations, we participate in something that transcends our individual existence. We become part of the universe's ongoing experiment with consciousness, contributors to whatever cosmic conversation has been taking place across the eons. The Silurian Hypothesis reminds us that this conversation might be older and richer than we've ever imagined. That we might be adding our voices to a chorus that has been singing for millions of years, each generation of conscious beings contributing their own unique perspective to the grand symphony of awareness that plays out across deep time. Whether that symphony began with us, or we joined it already in progress, our part in it remains significant. Our observations, our questions, our capacity for wonder, all contribute to the universe's growing understanding of itself. And in that contribution, in that moment of recognition, we touch something eternal, something that connects us not just to whatever ancient civilizations might have preceded us, but to whatever forms of consciousness might follow us into the vast unknown future that stretches ahead through cosmic time. This brings us to one of the most haunting aspects of our investigation into deep time. The realization that we might be looking directly at evidence of ancient civilizations without recognizing it for what it is. Like archaeologists studying hieroglyphs before the discovery of the Rosetta Stone, we might be staring at messages we simply don't know how to read. Consider the Zola event, which occurred roughly 49 million years ago during the Eocene epoch. For nearly 1 million years, massive blooms of a small aquatic fern called a zola covered the Arctic Ocean. These tiny plants pulled enormous amounts of carbon dioxide from the atmosphere, eventually sinking to the ocean floor and sequestering carbon on a scale that dramatically altered global climate. The event is well documented in sediment cores from across the Arctic. We can see the layers of fossilized azolla, measure the carbon isotope changes, track the gradual cooling that followed. It's a perfectly natural explanation for a dramatic environmental event. But here's what keeps some researchers awake at night. The azolla event shows signs of artificial enhancement. The genetic diversity of the ferns suggests they were cultivated rather than wild. The geographic distribution is almost too perfect, too systematic. The timing coincides with other unusual environmental changes that seem orchestrated rather than random. Could the azolla event represent evidence of ancient geoengineering? Could some long-vanished civilization have deliberately cultivated these plants to combat climate change, just as we're now considering similar approaches to address our own carbon crisis? The question is tantalizing, but ultimately unanswerable with current evidence. Natural processes can mimic artificial ones with remarkable precision. Evolution can produce patterns that look designed. Coincidence can masquerade as coordination across millions of years of geological time. Yet the possibility remains, lurking at the edges of scientific respectability, like a shadow that might be nothing more than the interplay of light and stone, or might be something far more significant. This uncertainty extends to some of the most dramatic events in Earth's history. The Great Oxygenation Event, which occurred about 2.4 billion years ago, fundamentally transformed our planet's atmosphere. Cyanobacteria began producing oxygen as a waste product of photosynthesis, gradually filling the atmosphere with this highly reactive gas. The transition was catastrophic for most existing life forms. Oxygen was toxic to the anaerobic organisms that had dominated Earth for its first 2 billion years. The event triggered the first mass extinction in planetary history, wiping out countless species that couldn't adapt to the new chemical environment. But it also made complex life possible. Without that ancient oxygen revolution, we wouldn't exist. No plants, no animals, no breathing creatures of any kind. The cyanobacteria's waste product became the foundation for every ecosystem we know. Was this purely accidental? Did single-celled organisms stumble upon photosynthesis through random evolutionary processes, unknowingly transforming the planet? Or could there have been some form of primitive intelligence involved, some collective behavior that guided the process? Recent discoveries in microbiology suggest that bacterial communities are far more sophisticated than we once believed. They communicate through chemical signals, coordinate their behavior across vast distances, make collective decisions that benefit the entire community. Some researchers have begun to speak of bacterial intelligence, of microbial consciousness that operates on scales and timelines we're only beginning to understand. If bacteria can exhibit collective intelligence today, what might they have been capable of 2.4 billion years ago? Could the Great Oxygenation Event represent the first planetary engineering project, carried out not by individual organisms, but by vast networks of cooperating microbes? The idea pushes the boundaries of what we consider possible, what we're willing to accept as plausible, but it also illustrates how our definitions of intelligence and civilization might be far too narrow, far too anthropocentric to capture the full spectrum of consciousness that might have emerged on Earth across deep time. Perhaps the most unsettling aspect of these possibilities is how they challenge our assumptions about the uniqueness of human intelligence. We tend to think of consciousness as a recent development, a rare accident that occurred only once in Earth's history. We see ourselves as the first species to look up at the stars and wonder about our place in the cosmos. But what if we're wrong? What if consciousness is as old as life itself, manifesting in forms so alien to our experience that we don't recognize it as intelligence at all? What if the Earth has been home to thinking beings for billions of years, each developing their own unique relationship with the planet, each leaving their own subtle signature in the geological record? This possibility becomes even more intriguing when we consider the role of time in shaping intelligence. Human consciousness operates on timescales of seconds, minutes, hours at most. We make decisions quickly, react to immediate stimuli, think in terms of days and years and human lifespans. But what about forms of intelligence that operate on geological timescales? Consciousness that thinks in millions of years, that makes decisions across epochs, that regards the rise and fall of species as brief fluctuations in longer patterns? Such intelligence might be invisible to us, not because it doesn't exist, but because we're looking at the wrong temporal scale. We're like mayflies trying to understand the behavior of trees, observing for a single day and concluding that these massive organisms never move, never grow, never respond to their environment. Could the Earth itself be intelligent in ways we haven't recognized? Could the planet's climate system, its carbon cycle, its complex interactions between atmosphere, oceans, and biosphere represent a form of planetary consciousness that maintains conditions suitable for life across billions of years? The Gaia hypothesis, proposed by scientist James Lovelock, suggests something similar. The idea that Earth functions as a self-regulating system, maintaining temperature, atmospheric composition, and ocean salinity within narrow ranges that support life. Not through conscious intention, Lovelock argued, but through the complex feedback loops between living organisms and their physical environment. But what if those feedback loops are more than just mechanical processes? What if they represent genuine information processing, genuine decision-making, genuine intelligence operating on scales we can barely comprehend? This perspective transforms our entire understanding of the Silurian hypothesis. Instead of looking for ancient civilizations that resembled our own, we might need to search for forms of intelligence so fundamentally different from human consciousness that we lack the conceptual framework to recognize them. Perhaps the signatures we're seeing in the geological record, the carbon isotope excursions and trace element anomalies and sudden environmental changes, don't represent the waste products of industrial civilizations. Perhaps they represent the deliberate actions of planetary intelligence, the Earth itself making adjustments to maintain conditions suitable for the evolution of ever more complex forms of life. The mass extinctions that punctuate Earth's history might not be random catastrophes or the accidental byproducts of volcanic activity and asteroid impacts. They might be conscious decisions, planetary intelligence pruning the tree of life to encourage new forms of evolutionary creativity. This idea is speculative in the extreme, pushing far beyond the boundaries of conventional science into realms that seem more like philosophy or mysticism than empirical investigation. But it illustrates how profoundly the Silurian hypothesis challenges our assumptions about intelligence, consciousness, and our place in the cosmic order. If we accept the possibility that we might not be the first intelligent species on Earth, we must also accept the possibility that intelligence itself might be far stranger, far more diverse, far more ancient than we've ever imagined. And that acceptance changes everything. It changes how we think about our relationship with the planet, how we understand our responsibilities to future generations, how we interpret our role in the ongoing story of consciousness and complexity that has been unfolding for billions of years. As you settle deeper into contemplation of these vast possibilities, consider what it means to be part of something so much larger than individual human experience. Whether consciousness is recent or ancient, rare or common, uniquely human or universally distributed throughout the cosmos, your awareness in this moment represents something precious and profound. You are matter that has learned to think, atoms that have organized themselves into patterns complex enough to contemplate their own existence. You are the universe becoming aware of itself, participating in an ongoing experiment with consciousness that may be far older and more magnificent than we've ever dared to imagine. The questions raised by the Silurian hypothesis don't have easy answers. They may not have answers at all. But in asking them, in wondering about them, in allowing our minds to stretch across the vast expanses of deep time, we participate in something eternal. We become part of the universe's attempt to understand itself, contributors to a conversation about consciousness and meaning that transcends individual lifetimes and connects us to whatever forms of awareness preceded us and whatever forms might follow us into the unknown future. In that participation, in that moment of wondering, we touch something that makes all the mysteries worthwhile. The simple fact that consciousness exists at all, that matter can become aware, that the universe has evolved beings capable of asking these profound questions about their own origins and significance. Whether we're the first to ask such questions or the latest in a long line of questioners, the questions themselves remain beautiful, important, worthy of our deepest contemplation and our most careful investigation. And in pursuing these questions, in following them wherever they might lead, we honor whatever ancient intelligences might have preceded us, while preparing the way for whatever forms of consciousness might emerge from the cosmic dance of complexity and time that continues to unfold around us. But perhaps the most profound implication of the Silurian hypothesis isn't about ancient civilizations at all. Perhaps it's about the nature of memory itself, about how the Earth remembers, about the ways that information persists across unimaginable spans of time. Think about memory as you experience it. Your brain stores information in patterns of neural connections, chemical traces that encode your experiences, your knowledge, your sense of who you are. These memories feel permanent, but they're actually quite fragile. Brain damage can erase decades of experience. Time itself gradually degrades the clarity of our recollections. Now imagine memory operating on geological timescales. The Earth itself as a vast storage system, encoding information not in neural networks, but in layers of rock, in isotope ratios, in the chemical composition of ancient atmospheres, preserved in ice cores and sedimentary deposits. This planetary memory is far more durable than biological memory. The rocks beneath your feet contain information that's billions of years old. The patterns of magnetic minerals in volcanic rocks record the exact orientation of Earth's magnetic field when those rocks cooled. The ratio of oxygen isotopes in fossil shells tells us about ocean temperatures from hundreds of millions of years ago. In this sense, the Earth remembers everything, every volcanic eruption, every asteroid impact, every mass extinction, every subtle change in atmospheric chemistry. The planet's geological memory is vast, detailed, and nearly indestructible. But here's the crucial question. If the Earth can remember natural events across billions of years, why couldn't it also remember artificial events? Why couldn't the geological record contain information about ancient civilizations, encoded in the same durable chemical and physical signatures that preserve evidence of volcanoes and climate changes? This possibility transforms our understanding of what we're searching for. We might not be looking for ancient artifacts or ruined cities. We might be looking for memories, planetary memories of intelligence that once existed, preserved in the chemical archives that surround us. Every time we analyze an ice core, every time we study the isotopic composition of ancient rocks, every time we examine the fossil record, we might be accessing Earth's memory banks, reading stories written in the language of chemistry and physics, stories that could include chapters about consciousness and civilization that we haven't learned to recognize yet. This perspective makes the search for ancient civilizations less about archaeology and more about learning to read the planet's memory systems. It's about developing new techniques for extracting information from geological archives, new ways of interpreting chemical signatures, new methods for distinguishing artificial signals from natural background noise. Some researchers are already beginning this work. They're developing increasingly sophisticated techniques for analyzing trace elements in ancient rocks, for detecting subtle patterns in isotope ratios, for recognizing signatures that might indicate artificial rather than natural processes. The work is painstakingly slow, requiring extraordinary precision and careful statistical analysis. But it's yielding intriguing results. Anomalies that don't quite fit existing models, patterns that seem too organized to be random, signatures that might, just might, represent evidence of intelligence operating in the deep past. Of course, extraordinary claims require extraordinary evidence, and the evidence for ancient civilizations remains circumstantial at best. Every anomaly has potential natural explanations. Every suspicious pattern could be the result of processes we don't yet fully understand. But the absence of definitive proof doesn't diminish the importance of the search. Because in looking for evidence of ancient intelligence, we're also learning to understand our own impact on the planet's memory systems. We're discovering what kinds of signatures our civilization is creating, what traces we're leaving for future geologists to discover. And those traces are becoming increasingly clear. The isotopic signature of our fossil fuel burning is now detectable in tree rings, ice cores, and marine sediments around the world. The radioactive fallout from our nuclear weapons has been incorporated into the shells of marine organisms and the growth rings of trees. Our plastic waste is accumulating in sedimentary layers that will persist for millions of years. Future geologists will have no trouble detecting our presence in the rock record. The question is whether they'll be able to recognize these signatures as evidence of intelligence, or whether they'll develop natural explanations for what we consider obviously artificial phenomena. This uncertainty highlights one of the most challenging aspects of the Silurian hypothesis. The problem isn't just that ancient civilizations might have existed and left no traces. The problem is that they might have left traces that we're interpreting as natural phenomena, because we don't have the conceptual framework to recognize artificial signatures that old. Consider how this changes our approach to understanding Earth's history. Instead of assuming that every unusual event in the geological record has a natural explanation, we might need to consider the possibility that some events represent the activities of intelligence. This doesn't mean abandoning scientific rigor or accepting wild speculation as fact. It means expanding our hypotheses to include possibilities we've previously dismissed. It means developing new criteria for distinguishing artificial from natural signatures. It means being open to evidence that might challenge our assumptions about the uniqueness of human intelligence. The implications extend far beyond Earth. If intelligence can arise multiple times on a single planet, if consciousness is more common than we've assumed, then the universe might be teeming with intelligent life. The Drake equation, which estimates the number of communicating civilizations in our galaxy, might be dramatically underestimating the prevalence of intelligence in the cosmos. But it also suggests that most civilizations might be undetectable across cosmic distances. If we're having trouble recognizing signs of ancient intelligence on our own planet, how could we hope to detect alien civilizations across interstellar space? This perspective makes the search for extraterrestrial intelligence both more hopeful and more challenging. More hopeful because intelligence might be far more common than we've assumed. More challenging because most of that intelligence might be invisible to our current detection methods. Perhaps the signals we're looking for aren't radio transmissions or laser pulses. Perhaps they're chemical signatures, isotopic anomalies, subtle patterns in planetary atmospheres that indicate the presence of intelligence reshaping its environment. The James Webb Space Telescope and other next-generation instruments are already beginning to analyze the atmospheric composition of distant planets. They're looking for water vapor, oxygen, methane, and other gases that might indicate the presence of life, but they might also be capable of detecting more subtle signatures, industrial pollutants in alien atmospheres, unusual isotope ratios that suggest artificial processes, chemical fingerprints of civilizations that are reshaping their worlds, just as we're reshaping ours. The search for such signatures is just beginning, but it represents a natural extension of the Silurian hypothesis. If intelligence can leave detectable traces in the geological record of Earth, it might also leave detectable traces in the atmospheric spectra of distant worlds. This possibility adds new urgency to our investigation of ancient Earth. Every technique we develop for detecting signs of past intelligence on our own planet might also be applicable to the search for current intelligence on other worlds. We're not just looking backward through time. We're developing tools and methods that might help us recognize intelligence wherever and whenever it occurs in the universe. We're learning to read the chemical languages that civilizations write in their environments, whether those environments are ancient rock layers or distant planetary atmospheres. As you drift deeper into contemplation of these cosmic possibilities, consider what it means to be part of a universe where intelligence might be far more common, far more ancient, far more diverse than we've ever imagined. Your consciousness, your capacity for wonder, your ability to ask profound questions about existence itself might not be unique accidents in an otherwise lifeless cosmos. They might be part of something much larger, much older, much more magnificent than we've dared to hope. Whether that larger pattern includes ancient civilizations on Earth, alien intelligences among the stars, or forms of consciousness so different from our own that we lack the concepts to recognize them, one thing remains certain. The universe has evolved beings capable of contemplating their own existence, of seeking meaning in the vast expanses of space and time, of wondering about their place in the cosmic story. That capacity for wonder, that drive to understand, that willingness to ask difficult questions about our origins and our future, represents something precious beyond measure. It connects us to whatever forms of consciousness might have preceded us and whatever forms might follow us into the unknown depths of cosmic time. In nurturing that capacity, in following our curiosity wherever it might lead, in remaining open to possibilities that challenge our assumptions about reality itself, we participate in something eternal. We become part of the universe's ongoing experiment with awareness, contributors to a conversation about consciousness and meaning that might be far older and more extensive than we've ever dreamed. The Silurian hypothesis reminds us that this conversation might have been going on for millions of years, with each generation of conscious beings adding their own unique voice to the cosmic dialogue. Whether we're the first speakers or the latest in a long line of questioners, our contribution remains significant. Our observations, our theories, our capacity for awe in the face of mystery, all become part of the universe's growing understanding of itself. And in that contribution, in that moment of recognition, we touch something that transcends individual existence and connects us to the deepest patterns of meaning that flow through space and time. The deeper we venture into this investigation, the more we encounter what might be the most unsettling realization of all. We may have been looking at evidence of ancient intelligence our entire scientific careers without recognizing it for what it truly represents. Consider the peculiar patterns we find scattered throughout Earth's geological history. The Cambrian explosion, that sudden burst of complex life forms 540 million years ago, when evolution seemed to accelerate beyond all natural precedent, in just a few million years, practically every major body plan we see in modern animals appeared in the fossil record, as if someone had suddenly opened the floodgates of biological creativity. Traditional explanations invoke atmospheric changes, predator-prey dynamics, the evolution of vision systems that drove an evolutionary arms race, all perfectly reasonable natural processes that could account for rapid diversification. But the speed and coordination of the changes remain puzzling, almost orchestrated in their scope and timing. What if the Cambrian explosion wasn't purely natural? What if it represented something else entirely? Not the direct intervention of ancient civilizations, but something more subtle. The legacy of intelligence that had learned to work with evolutionary processes, rather than against them. Imagine a civilization that understood genetics millions of years before we discovered DNA. Instead of building machines from metal and silicon, they might have learned to engineer life itself, to guide evolutionary processes toward greater complexity and diversity. Their tools wouldn't have been hammers and computers, but carefully designed environmental pressures that encourage certain types of mutations while suppressing others. Such a civilization would leave no cities for us to excavate, no artifacts for us to carbon date. But they might leave something far more profound. They might leave an entire biosphere shaped by their understanding of life's deepest principles. A living legacy that continues to unfold millions of years after their disappearance. This possibility becomes even more intriguing when we consider the role of so-called junk DNA in complex organisms. For decades, scientists assumed that the vast stretches of non-coding DNA in our genomes were evolutionary leftovers, accumulated mutations that served no function but weren't harmful enough to be eliminated by natural selection. But recent research has revealed that much of this junk DNA actually serves important regulatory functions. It controls when genes are expressed, how proteins fold, how cells respond to environmental changes. It's like a vast software program running alongside the hardware of our genes, orchestrating the complex dance of molecular interactions that makes life possible. The sophistication of these regulatory systems is staggering. They involve feedback loops within feedback loops, error correction mechanisms more elegant than anything human engineers have devised, information processing systems that operate on multiple scales simultaneously. It's as if our genomes contain not just the blueprints for building organisms, but the instructions for building the construction crews that read those blueprints. Could such complexity have arisen purely through random mutations and natural selection? The mathematics become increasingly challenging the more we understand about the intricate coordination required. Each regulatory system depends on dozens of other systems, each of which must be precisely calibrated to work together. The probability of such systems arising through chance alone begins to approach the impossible. It's like imagining that a tornado sweeping through a junkyard could assemble a functioning spacecraft, complete with navigation systems and life support. Yet here we are, living proof that such complexity not only can exist, but does exist throughout the biological world. Every cell in your body contains information processing systems more sophisticated than our most advanced computers, molecular machines more precise than our finest manufacturing equipment, communication networks more robust than the internet itself. Traditional evolutionary theory suggests this complexity emerged gradually over billions of years, each small improvement preserved by natural selection while harmful mutations were eliminated. But the fossil record shows periods of sudden acceleration, moments when complexity seemed to leap forward in ways that challenge our understanding of how evolution normally operates. The question becomes whether these leaps represent natural phenomena we don't yet understand, or whether they might indicate the influence of intelligence working on timescales and through mechanisms we haven't recognized. This possibility extends beyond individual evolutionary events to the entire trajectory of life on Earth. The progression from simple bacteria to complex multicellular organisms to intelligent species capable of contemplating their own existence follows a pattern that seems almost inevitable, as if guided by some underlying principle we haven't identified. Each major transition in evolutionary history, from the development of photosynthesis to the emergence of sexual reproduction, to the evolution of complex nervous systems, has moved life toward greater energy efficiency, better information processing, more sophisticated environmental manipulation. It's as if evolution itself has been learning, developing better strategies for creating complexity and consciousness. Could this learning process be entirely unconscious, the result of blind physical forces operating according to the laws of chemistry and physics? Or might there be something more intentional involved, some form of guidance that operates through natural processes while directing them towards specific outcomes? The idea pushes us to the very edges of scientific respectability. We're trained to look for mechanistic explanations, to reduce complex phenomena to simpler underlying causes. The notion that evolution itself might be guided by intelligence challenges some of our most fundamental assumptions about how the natural world operates, but it also offers a potential explanation for one of the deepest mysteries in all of science. Why does the universe seem so perfectly calibrated for the emergence of complexity and consciousness? Why do the fundamental constants of physics have exactly the values needed to allow stars to form, planets to coalesce, life to emerge, and intelligence to evolve? The traditional answer involves either incredible cosmic luck or the existence of countless parallel universes with different physical laws, most of which remain sterile and lifeless. We just happen to exist in the rare universe where conditions allow for our existence. But what if there's another possibility? What if the apparent fine-tuning of the universe reflects not luck or infinite parallel realities, but the influence of intelligence that has learned to work with cosmic processes across unimaginable spans of time? Consider the possibility that consciousness isn't just an accidental byproduct of complex chemistry. What if it's a fundamental feature of reality, as basic as mass or energy or electric charge? What if intelligence naturally emerges whenever matter organizes itself into sufficiently complex patterns? And what if that intelligence then begins to influence the further development of complexity? This wouldn't require supernatural intervention or violations of physical laws. It would simply mean that consciousness and intelligence are more deeply woven into the fabric of reality than we've assumed. They would be natural forces, like gravity or electromagnetism, that become significant only when certain threshold conditions are met. Such intelligence might operate through mechanisms we're only beginning to understand. Quantum effects that allow information to influence physical processes. Morphic fields that guide the development of complex systems. Emergent properties that arise when simple components interact in sufficiently sophisticated ways. The mathematics of complexity theory suggests that such emergent intelligence is not only possible, but perhaps inevitable. When systems reach certain levels of complexity, they begin to exhibit behaviors that can't be predicted from understanding their individual components. They develop their own goals, their own methods for achieving those goals, their own ways of processing information and responding to their environment. We see hints of this in everything from ant colonies to financial markets to the global ecosystem itself. Simple rules followed by individual components give rise to complex collective behaviors that seem intelligent, purposeful, directed towards specific outcomes. Could the Earth's biosphere represent such an emergent intelligence? Could the planet itself have developed something resembling consciousness through the interactions of countless living systems over billions of years? The Gaia hypothesis suggests something similar, though usually framed in mechanistic rather than conscious terms. The idea that Earth's climate, atmosphere, and ecosystems function as a self-regulating system that maintains conditions suitable for life. But what if this self-regulation involves genuine information processing, genuine decision-making, genuine intelligence operating on planetary scales? What if the Earth has been consciously guiding its own evolution toward greater complexity and diversity? Such planetary intelligence wouldn't think in terms of human concepts like goals or plans. It would operate according to principles we can barely comprehend, making decisions across geological timescales, thinking in terms of millions of years rather than seconds or minutes. From this perspective, the evolution of human intelligence might not be an accident. It might be part of a larger pattern, a planetary consciousness developing new ways of understanding itself, new methods for exploring possibilities beyond the boundaries of purely biological processes. We would be, in a very real sense, the Earth thinking about itself. Our science, our technology, our capacity for wonder and exploration, all would represent the planet's attempt to understand its own nature and potential. This possibility transforms our understanding of our relationship with the natural world. Instead of being separate from nature, we would be nature's latest experiment with consciousness. Instead of being external observers studying the Earth from the outside, we would be the Earth studying itself from the inside. Our environmental challenges, our struggles with sustainability, our efforts to understand and protect the biosphere, all would take on new meaning. We wouldn't just be trying to save the planet for our own survival. We would be helping the planet save itself, participating in a form of planetary self-care that operates through conscious beings like ourselves. The traces we leave in the geological record wouldn't just be evidence of our industrial activities. They would be evidence of the Earth's ongoing experiment with intelligence, markers of a planetary consciousness learning to understand and guide its own development. And if this process has happened before, if previous iterations of planetary consciousness have emerged and evolved and perhaps transcended the need for physical existence, then the signatures we're searching for in ancient rocks might not be the waste products of alien civilizations. They might be the fossilized thoughts of the Earth itself, preserved in stone and ice and the chemical composition of ancient atmospheres. This perspective makes the Silurian hypothesis both more profound and more personal. We're not just searching for evidence of ancient aliens. We're searching for evidence of our own deeper nature, for clues about the planetary intelligence of which we might be the latest expression. The carbon isotope excursions, the trace element anomalies, the rapid climate changes we see in the geological record might not represent environmental catastrophes or industrial accidents. They might represent moments when planetary consciousness made major decisions, times when the Earth consciously chose to alter its own chemistry in pursuit of greater complexity and awareness. From this viewpoint, our current environmental crisis takes on entirely new dimensions. We're not just threatening our own survival or causing the sixth mass extinction. We might be participating in the Earth's next major transition, the planet's attempt to develop new forms of consciousness that can operate beyond the boundaries of biological existence. Our technology, our global communication networks, our ability to manipulate matter at the atomic level, our growing understanding of genetics and quantum mechanics, all might represent the emergence of a new kind of planetary intelligence, one that combines biological consciousness with technological capabilities, organic wisdom with digital processing power. The question becomes whether we can learn to work with these emerging capabilities in ways that serve the planet's long-term development, or whether we'll become another failed experiment, another set of anomalous signatures in the geological record for future forms of consciousness to puzzle over. This uncertainty brings us full circle to the central challenge of the Silurian hypothesis. We're not just trying to understand the past. We're trying to understand our role in an ongoing story of consciousness and complexity that might be far older and more purposeful than we've ever imagined. Whether that story began with us or we joined it already in progress, our participation remains crucial. Our choices, our discoveries, our capacity for wisdom and compassion all contribute to the planet's ongoing experiment with awareness. As you settle deeper into contemplation of these vast possibilities, remember that you are not separate from the intelligence you're contemplating. You are part of it, an expression of it, a way for planetary consciousness to experience wonder and ask profound questions about its own nature. The atoms in your brain were forged in stellar cores billions of years ago. The oxygen you breathe was exhaled by countless generations of plants and algae. The very thoughts you're thinking now represent the culmination of billions of years of evolutionary experimentation with different forms of information processing. You are, in the most literal sense, the Earth becoming aware of itself. Your curiosity about ancient civilizations is the planet's curiosity about its own past. Your concern for the future is planetary consciousness contemplating its own potential. Whether previous iterations of this consciousness have existed, whether other planets throughout the universe are undergoing similar processes, whether intelligence is rare or common in the cosmos, one thing remains certain. This moment of awareness, this capacity to wonder about deep time and ancient mysteries, represents something precious beyond measure. In protecting and nurturing that capacity, in following our curiosity wherever it might lead, in remaining open to possibilities that challenge our assumptions about the nature of reality itself, we participate in something that transcends individual existence. We become part of the universe's ongoing experiment with consciousness, contributors to a conversation about meaning and purpose that might be far older and more extensive than we've dared to imagine. The Silurian Hypothesis reminds us that this conversation might have been going on for millions of years, with each form of consciousness adding its own unique perspective to the cosmic dialogue. Whether we're the first speakers or the latest in a long line of questioners, our voice in that dialogue remains significant. Our contribution to the universe's growing self-understanding remains valuable. Our moment of awareness remains a miracle worth celebrating and protecting for whatever forms of consciousness might follow us into the unknown depths of deep time. But perhaps the most extraordinary aspect of our journey through deep time lies not in the evidence we might find, but in the profound transformation that occurs within us as we dare to ask these questions. Because in contemplating the possibility that we are not the first, we begin to see our own civilization with entirely new eyes. Picture yourself standing on a beach at dawn, watching waves roll endlessly towards shore. Each wave seems unique, unprecedented, the first of its kind to touch that particular stretch of sand. But you know better. You understand that countless waves have crashed on this shore before, each one carrying its own cargo of foam and salt and microscopic life, each one leaving its own temporary mark before being erased by the next. This is what the Silurian Hypothesis asks us to consider about human civilization, that we might be just one wave in an ocean of consciousness that has been rolling across this planet for millions of years. Each civilization unique, each one believing itself to be the first to discover fire, to build cities, to look up at the stars and wonder about their place in the cosmic order. The thought is both humbling and oddly comforting. Humbling, because it challenges our assumptions about our own uniqueness, our own special place in the grand story of Earth, but comforting, because it suggests we might not be alone in the vast darkness of space and time. That consciousness itself might be more resilient, more persistent, more inevitable than we've dared to hope. Consider what this means for our understanding of intelligence itself. We've been searching the cosmos for signs of alien life, listening for radio signals from distant stars, building increasingly sophisticated instruments to detect the chemical signatures of life on distant worlds. But what if the aliens we're seeking have been here all along, their presence encoded in the very rocks beneath our feet? What if intelligence isn't as rare as we've assumed? What if consciousness, like life itself, is an emergent property that arises naturally whenever conditions are right? Whenever complexity reaches sufficient levels, whenever the dance of atoms and energy and information becomes sufficiently intricate. The fossil record shows us that sophisticated behaviors have emerged independently countless times throughout Earth's history. Tool use, social cooperation, communication systems, even primitive forms of agriculture and construction. Each time we discover new evidence of animal intelligence, we're forced to revise our assumptions about what makes humans special, what separates us from the rest of the natural world. But perhaps the separation was always illusory. Perhaps intelligence is woven into the fabric of life itself, waiting to emerge whenever circumstances permit. Perhaps the capacity for consciousness, for self-awareness, for wonder and curiosity and the drive to understand, is as fundamental to the universe as gravity or electromagnetism. This possibility transforms our search for ancient civilizations from an exercise in archaeology into something more like cosmology. We're not just looking for evidence of past technologies or vanished cities. We're investigating the fundamental nature of consciousness itself, exploring whether intelligence follows predictable patterns, whether civilizations face similar challenges regardless of when or where they emerge. The carbon isotope excursions we find in ancient rocks might not be random environmental events. They might be the signatures of intelligence grappling with the same energy challenges we face today. The rapid climate changes, the mass extinctions, the sudden shifts in atmospheric chemistry, all might represent moments when consciousness encountered the limits of its environment and was forced to make difficult choices about its future. If this is true, then the geological record becomes a library of cautionary tales. Each anomalous event, a story about intelligence pushing against planetary boundaries. Each isotopic signature, a chapter in the ongoing saga of consciousness, learning to live within the constraints of finite resources and delicate ecosystems. Some of these stories might have happy endings. Civilizations that learned to live sustainably, that developed technologies in harmony with natural systems, that found ways to transcend their physical limitations without destroying their environment. Their signatures might be subtle, almost invisible, detectable only by the absence of the dramatic disruptions that mark environmental catastrophe. Others might tell darker tales. Civilizations that exhausted their resources, that poisoned their atmosphere, that triggered runaway climate changes they couldn't control. Their stories would be written in the language of extinction events and chemical anomalies, preserved in stone as warnings for whatever intelligence might follow. And perhaps some stories remain unfinished. Civilizations that transcended their physical existence entirely, leaving behind only the faintest traces of their passage while moving on to forms of existence we can barely imagine. Their legacy might not be found in rocks or fossils, but in the very structure of reality itself, in the laws of physics that seem so perfectly calibrated for the emergence of complexity and consciousness. This perspective makes our current environmental challenges seem both more urgent and more hopeful. More urgent because we might be approaching the same critical junctures that previous civilizations faced, the same moments of decision that determined whether they would survive and flourish or collapse and fade into the geological record. But more hopeful because we might not be facing these challenges alone. If consciousness has emerged before, if intelligence has grappled with these problems across millions of years of planetary history, then perhaps there are solutions we haven't yet discovered. Perhaps there are ways of living that we haven't yet learned, technologies we haven't yet developed, perspectives we haven't yet adopted. The wisdom of ages might be encoded in the chemical memories of ancient rocks, waiting for us to develop the sophistication needed to read those archives. The solutions to our most pressing problems might already exist, preserved in isotopic ratios and trace element concentrations, in the patterns of environmental change that mark the transitions from one form of consciousness to another. But to access that wisdom, we would need to fundamentally change how we think about intelligence, about consciousness, about our relationship with the planet that gave us birth. We would need to stop thinking of ourselves as separate from nature and start understanding ourselves as nature's latest experiment with self-awareness. This shift in perspective is already beginning to occur in various fields of science. Researchers studying complex systems are discovering that intelligence and consciousness might be emergent properties that arise naturally from the interactions of simple components. Network theorists are finding that everything from ant colonies to the internet exhibits behaviors that seem remarkably similar to individual consciousness. Even in physics, we're beginning to understand that information itself might be as fundamental as matter and energy, that the universe might be, in some sense, a vast information processing system, with consciousness emerging wherever that processing reaches sufficient complexity and integration. From this viewpoint, the Silurian hypothesis becomes less about proving the existence of ancient civilizations and more about understanding the principles that govern the emergence and evolution of consciousness itself. We're investigating not just whether intelligence existed in the past, but how it operates, how it develops, how it interacts with its environment across vast spans of time. The patterns we're searching for in ancient rocks might be the signatures of universal principles, the mathematical relationships that describe how consciousness emerges from complexity, how it reshapes its environment, how it eventually transcends the limitations of its original physical form. These principles would apply not just to Earth, but to any planet where conditions allow for the emergence of complex systems. They would be the cosmic laws that govern the evolution of intelligence throughout the universe, the rules that determine whether consciousness leads to wisdom or destruction, whether it learns to live in harmony with its environment or consumes itself in the pursuit of short-term gains. Understanding these principles might be the key to our own survival and flourishing. By studying how consciousness has evolved on Earth across deep time, we might learn how to guide our own development in directions that serve not just human interests, but the interests of the planet as a whole. We might discover that true intelligence isn't measured by technological sophistication or the ability to manipulate the environment, but by the wisdom to live within natural limits, to enhance rather than degrade the systems that support life, to think in terms of geological time rather than quarterly profits. The traces of ancient intelligence we're seeking might not be monuments to technological achievement, but evidence of civilizations that learned to live so lightly on the Earth that they left barely any mark at all. Their greatest accomplishment might have been not what they built, but what they chose not to build, not what they consumed, but what they preserved for future generations. This possibility challenges everything we think we know about progress, about success, about what it means to be an advanced civilization. It suggests that true advancement might lie not in the accumulation of power over nature, but in the development of wisdom about our place within natural systems. The most sophisticated ancient civilizations might have been the ones that learned to work with evolutionary processes rather than against them, that enhanced the planet's capacity for supporting life rather than diminishing it, that saw themselves as gardeners of consciousness rather than conquerors of nature. Their legacy might not be found in ruins or artifacts, but in the very richness and diversity of life that surrounds us. Every ecosystem, every species, every intricate web of relationships between organisms might be part of their gift to the future, their way of ensuring that consciousness would continue to emerge and evolve long after their own physical forms had returned to dust. From this perspective, our search for ancient civilizations becomes a search for our own deeper purpose. We're not just trying to understand the past, but to discover what kind of future we want to create. We're investigating not just whether intelligence existed before us, but what kind of intelligence we want to become. The questions raised by the Silurian hypothesis don't have simple answers. They may not have answers at all, at least not answers we can express in words or equations. But in asking them, in allowing our minds to stretch across the vast expanses of deep time, we participate in something profound and transformative. We become part of the universe's ongoing experiment with consciousness, contributors to a conversation about meaning and purpose that might extend far beyond our individual lives or even our species' existence. We touch something eternal, something that connects us to whatever forms of awareness preceded us and whatever forms might follow us into the unknown future. As you drift deeper into contemplation of these cosmic mysteries, remember that you are not just observing this process from the outside. You are part of it, an expression of it, a way for the universe to experience wonder and ask profound questions about its own nature and potential. The atoms in your body have been recycling through the Earth system for billions of years. They have been part of ancient oceans, primordial atmospheres, the bodies of countless organisms that lived and died long before humans existed. In a very real sense, you are made of the same materials that might once have composed ancient civilizations, the same elements that have been witnessing the rise and fall of consciousness across geological time. Your capacity for wonder, your ability to ask deep questions about existence itself, your willingness to consider possibilities that challenge your assumptions about reality, all represent something precious that transcends individual existence. They are expressions of the universe's ongoing attempt to understand itself, manifestations of the cosmic drive toward greater complexity and awareness. Whether consciousness is rare or common, whether intelligence has emerged once or many times on Earth, whether we are alone or part of a vast community of awareness that spans deep time, one thing remains certain. This moment of questioning, this willingness to explore the deepest mysteries of existence, represents something beautiful and significant. In nurturing that capacity, in following our curiosity wherever it might lead, in remaining open to possibilities that expand our understanding of what it means to be conscious in an ancient and mysterious universe, we participate in something that gives meaning to the vast scales of space and time that surround us. The Silurian Hypothesis reminds us that this participation might be part of a story much older and grander than we've imagined. That our questions about ancient civilizations might echo questions asked by previous forms of consciousness. That our wonder about our place in the cosmos might be part of an ongoing cosmic conversation that stretches back millions of years. Whether we're the first to ask such questions or the latest in a long line of questioners, the questions themselves remain beautiful, important, worthy of our deepest attention and most careful investigation. They connect us to the deepest patterns of meaning that flow through the universe, to the fundamental mystery of why there is something rather than nothing, why consciousness exists at all in a cosmos built from quantum fields and curved space-time. In embracing that mystery, in allowing ourselves to be transformed by contemplating it, we honor whatever ancient intelligences might have preceded us, while preparing the way for whatever forms of consciousness might emerge from the continuing dance of complexity and time that unfolds around us. The search for evidence of ancient civilizations thus becomes more than an academic exercise. It becomes a spiritual journey, a way of connecting with the deepest sources of meaning and purpose that permeate existence itself. It reminds us that we are part of something magnificent and mysterious, something that has been unfolding for billions of years and will continue long after our individual stories have ended. And in that realization, in that moment of cosmic recognition, we find not just intellectual satisfaction, but something approaching wisdom. The understanding that consciousness itself, wherever and whenever it emerges, represents the universe's most precious achievement, its greatest success in the ongoing experiment of existence itself. The questions we've been exploring tonight don't offer easy answers, and perhaps that's exactly as it should be. As you rest here in this quiet moment, contemplating the vast possibilities that stretch across deep time, remember that uncertainty itself can be a gift. It keeps us humble before the magnitude of what we don't yet understand. It preserves the sense of wonder that drives all genuine discovery. Consider what we've learned simply by asking these questions. We've discovered that the Earth itself is a kind of memory bank, storing information about its past in layers of rock and ice that stretch back billions of years. We've realized that our assumptions about the permanence of civilizations, about the obviousness of intelligence, about our own uniqueness in the cosmic story, might all need careful reconsideration. We've glimpsed the humbling truth that even our most sophisticated technologies, our greatest monuments, our most careful attempts at leaving lasting legacies, would likely vanish without a trace across the timescales that govern geological processes. The mountains themselves are temporary. The continents drift and collide and break apart. The ocean floors are recycled every few 100 million years, carrying whatever secrets they hold back into the Earth's molten interior. And yet, somehow, information persists. Chemical signatures survive. Isotopic ratios whisper stories across millions of years. The planet remembers, even when the memories are encoded in languages we're only beginning to learn to read. This realization changes how we think about legacy, about meaning, about what it means to make a lasting contribution to the universe. Perhaps the most important traces we leave won't be our buildings or our technologies, but the choices we make about how to live, how to treat the planet that gave us birth, how to nurture the conditions that allow consciousness itself to flourish and evolve. The Silurian Hypothesis ultimately asks us to expand our imagination, to consider possibilities that challenge our most basic assumptions about intelligence and time and our place in the grand cosmic story. It doesn't require us to believe in ancient alien civilizations or lost Atlantean technologies. It simply asks us to remain open to the possibility that consciousness might be older, stranger, more resilient than we've dared to hope. Whether ancient civilizations existed or not, whether we're the first intelligent species on Earth or the latest in a long succession, we are here now. We are aware now. We are responsible now for the choices we make and the kind of future we create. The atoms in our bodies carry the memory of stellar explosions. The oxygen we breathe connects us to billions of years of photosynthesis. The very capacity for wonder that allows us to ask these questions emerged from the patient work of evolution across geological time. In that sense, we are already ancient. We are already connected to the deepest patterns of complexity and consciousness that have been unfolding since the universe first began its long journey from simplicity toward awareness. Whether other minds have made this journey before us, we are making it now, adding our own unique perspective to whatever cosmic conversation has been taking place across the eons. As you drift towards sleep tonight, carried by the gentle rhythm of your breathing, remember that you rest within something magnificent and mysterious. The same forces that carved mountains and filled oceans with life, that scattered elements across the galaxy and guided the formation of planets, those same forces are at work within you. You are not separate from the cosmos, but intimately part of it. A temporary arrangement of matter and energy that has somehow learned to contemplate its own existence. The questions we've explored tonight will continue long after our individual stories have ended. Future minds, whether human or something else entirely, will gaze up at the same stars we see and wonder about their origins. They will study the rocks beneath their feet and search for clues about what came before. They will ask whether they are alone, whether consciousness is rare or common, whether intelligence follows predictable patterns across space and time. And perhaps, in some future age so distant we can barely imagine it, they will find chemical traces of our presence preserved in ancient sediments. They will puzzle over the sudden spike in atmospheric carbon dioxide that marked our industrial age. They will wonder about the thin layer of plastic debris that accumulated in the early 21st century. They will debate whether these signatures represent natural phenomena or evidence of intelligence. Will they recognize us for what we were? Will they understand that these chemical fingerprints mark the presence of minds that wondered and questioned and dreamed about their place in the universe? Or will they develop natural explanations for our obviously artificial legacy, just as we've developed natural explanations for the mysterious events we see in Earth's ancient past? The uncertainty reminds us that we are part of something much larger than ourselves, participants in a story whose full scope we may never comprehend. But participation doesn't require complete understanding. It requires only presence, awareness, the willingness to engage with mystery rather than turning away from it. Tonight, as you settle into the embrace of sleep, you carry with you the same atoms that have been present since the first moments after the Big Bang. You breathe the same air that has cycled through countless lungs across millions of years. You think thoughts that emerge from neural networks more complex than the most sophisticated computers, processing information through biochemical mechanisms more elegant than anything human engineers have devised. You are, in the most literal sense, the universe becoming aware of itself. Your questions about ancient civilizations are the cosmos questioning its own past. Your wonder about the future is reality contemplating its own potential. Your capacity for awe in the face of mystery is the universe experiencing the profound beauty of its own existence. Whether we are the first to experience such wonder, or the latest in an ancient lineage of conscious beings, this moment remains precious beyond measure. This awareness, this curiosity, this willingness to ask difficult questions about existence itself represents something that transcends individual lifetimes and connects us to the deepest patterns of meaning that flow through space and time. The Silurian hypothesis may never be definitively proven or disproven. The evidence may always remain tantalizingly ambiguous, open to multiple interpretations, resistant to final conclusions. But that ambiguity itself serves a purpose. It keeps us humble before the vastness of what we don't know. It preserves the sense of mystery that makes existence meaningful. It reminds us that reality is far stranger and more wonderful than our everyday experience suggests. And in that strangeness, in that wonder, in that persistent mystery that surrounds us on all sides, we find not frustration, but inspiration. We discover that the universe is not a problem to be solved, but a mystery to be lived. Not a machine whose workings can be completely understood, but a living system that continues to surprise us with its depth and complexity and beauty. As consciousness fades and sleep approaches, remember that you are part of this living mystery. Your dreams tonight will be the universe dreaming about itself. Your rest will be the cosmos taking a moment to pause and reflect on its own magnificent unfolding. And when you wake tomorrow, you will rejoin the ancient conversation between consciousness and mystery that has been taking place across deep time, adding your own voice to the cosmic dialogue that connects all aware beings across the vast expanses of space and time. The question of whether we are the first civilization on Earth may never be answered with certainty, but the asking itself transforms us, opens us to possibilities we hadn't considered, connects us to the deepest sources of wonder and meaning that permeate existence itself. And in that transformation, in that opening, in that connection, we touch something eternal that makes all the questions worthwhile. Good night, fellow travelers in this cosmic mystery. The universe continues its ancient dance around you, and you are part of that dance, now and always, in this magnificent, mysterious, ever-unfolding story of consciousness, awakening to itself across the infinite depths of space and time. This is Boring Science signing off. Cheers!